Last class, we talked about signals, noise, and filtering to isolate signals from noise. We focused on a familiar filter, which is the RC filter, a resistor and a capacitor. Depending on how you arrange the input and output on the RC filter, it can act as a high-pass filter, so passing high frequencies and attenuating low frequencies, or the reverse. It can act as a low-pass filter, passing through low frequencies and attenuating high frequencies. In today's class, I want to move on from implementing the low-high RC filter to other types of filters. We'll look at filters in both the time domain, and we'll look at filters also in the frequency domain. We'll look at some important in terms of being used, being applied in all sorts of situations in physics, in all sorts of situations in engineering. Types of filters. We'll look at what's called a Hann filter, a Hamming filter. They're applied in the time domain. And we'll also look at what are called a brickwall filter and a carpet cleaning filter. They're applied in the frequency domain. So we'll get to see the scope of filtering that's done of signals and noise across physics and engineering. I just wanted to mention one classic example of filtering, and it was the detection of gravitational waves in the LIGO experiment. You probably know that the LIGO experiment involves two setups of perpendicular arms in which laser light is directed along these kilometer-long arms, and a interference pattern of the two beams of laser light is produced. Any changes in the length of the arms, for example, due to a gravitational wave passing through, will cause a change in the interference pattern. And the challenge is that the signal of gravitational waves is a tiny, tiny, tiny weak signal. It's overwhelmed by a background of noise from all sorts of sources, from road traffic to earthquakes, to all sorts of things. And so the problem is to pick out the tiny gravitational chirp from gravitational waves from the background noise. And filtering was used to do that. Filtering is used to very effectively do that. They filtered out a region of frequencies that run from some tens of hertz to some hundreds of hertz to pick out the gravitational wave signal. Okay, last class we talked about RC filters. We talked about the low pass filter. I just want to remind us of that quickly as we're going to move on. When we implemented the low pass RC filter digitally, we realized that it was implemented in a rather simple way. It became a simple recursive filter digitally, in which the current output sample was determined by the current input sample and the previous output sample. It was just a combination of those two. Here it is. The current output sample depends on the current input sample and the previous output sample. That's the feedback. And the weighting of those two contributions just depends on your RC time constant. We explore that filter digitally in three different responses. We explored it in the frequency response, how it attenuated or passed signals depending on the frequency of the signals. We also explored it through step responses and impulse responses, and here's just the plot that we made in the last class. We didn't do this for the high pass filter, but here is how an equivalent program will work for the high pass filter. For the high pass filter, the current value of the output is determined by the previous value of the output and the change in the input. So that's the difference there for the high pass filter. And again, the weighting of those two contributions to the output in this recursive filter is determined by the RC time constant that you have picked. These are the corresponding frequency, impulse, and step function responses for the high pass filter. So the action of implementing this recursive filter here, and you see for the high pass filter, of course, it would pass higher frequencies and it would attenuate lower frequencies. For the impulse or the step function, you see the effect of the change. It's the change that gets through the filter for a high pass filter. I just wanted to say that so elimination with the simple RC low pass filter or the simple high pass RC filter is that the transition from passing a signal to attenuating the signal is a relatively slow transition. So if you have a low pass filter, you're going to pass low frequency signals, you're going to attenuate high frequency signals, but the transition from the passing to the attenuation is spread over a wide frequency range. And likewise for the high pass filter, you're going to pass high frequencies, you're going to attenuate low frequencies, but there's a broad transition between the attenuation and the passing of the signals. You can arrange for basically a ladder or a sequence of simple RC filters. So you can have one RC filter followed by another RC filter followed by another RC filter. What's the effect of that? Well, the effect of that is basically to steepen and shorten the transition region from passing the signal through the filter to attenuating the signal with the filter. So if instead of using just one RC low pass filter, I construct a series of low pass RC filters in series with one another. This is just a picture of two of them in series with one another, but you could imagine a whole ladder of these arrangements in series with one another. The effect is to make steeper and steeper and steeper as you add more and more rungs to the ladder, the transition from passing the signal to attenuating the signal, which is typically what you want to do. You want to pass your signal, you want to attenuate your noise, you want a steep transition between the noise and the signal. So this is one way that you can do it with analog circuits, and you can also do it digitally. You can write down a digital recursion relation like we did for the simple RC circuits. You can write it down for this ladder circuit. It's actually kind of interesting because you end up with an equation for the digital ladder RC circuit that is the same equation as we actually met earlier on for the solution of the diffusion equation. So you get the same solutions out of those two problems. I don't have a sort of deep understanding of why that is, but the code that we have used for the diffusion equation could be turned into the code for a ladder RC circuit. Okay, so let's move on to some different types of filters. So, the RC filters we were looking at were recursive filters. The ladder circuit that we just looked at, that would be a recursive filter. The output for a given sample is determined by the input samples and the prior output samples. The recursive filters have feedback. I'm going to turn now to convoluting filters, in which the output sample is just determined by the prior input samples and doesn't have, but it's just determined by input samples, doesn't have feedback from the prior output sample. So we're going to talk about window filters, which are commonly used in signal processing. A simple way of thinking about a window filter is that some window function, and we'll talk about what sort of window functions, but some window function is applied to the signal input, the input to the filter, and that window function is convoluted with the input, and that becomes the output of the window filter. And so these window filters are like viewing the signal through this window, through convolution with this window. So the simplest case would be what's called a rolling average filter. Rolling average is a very simple window in which I've written it down here on the slide here. The window is just a number of samples, contiguous consecutive number of samples, and we're just going to average the output, average the input over the number of samples to calculate the output. So it becomes like a rolling average of the input. And you can adjust that rolling average to be however many samples you want the rolling average to be. So in this little example here, in blue, I'm imagining my input. In red is my output. And my output is just derived as a rolling average of the, this case, neighboring 10 samples on the input. So every sample on the output, which of this sample is the output, then this is an average of the 10 neighboring samples around that output sample. So 5 samples to the left and 5 samples to the right. And that's a rolling average filter. You can see that rolling average filter and imagine what it's doing. And see what it's doing on this plot. It's letting through a low frequency signal. There is a low frequency sine wave here. That signal comes through the rolling filter smoothly, but it's filtering out the high frequency noise. So there's some high frequency noise on a blue plot and an input signal, and that's filtered out, largely filtered out by the rolling average filter. So just like the RC low pass filter was derived to pass low frequencies and attenuate high frequencies, this rolling average filter, which is a different algorithm, is also passing low frequencies and attenuating high frequencies. So it's doing a similar job. The rolling average filter is just averaging the nearby samples, the neighboring samples on the input with equal volume. So it just takes a ordinary, regular average of the samples in your window. And that produces a filter. You can improve that filter, meaning that you can improve the transition between passing a signal and attenuating the signal by taking a weighted average of the samples in your window. So instead of just weighting each sample in your input window equally, you can weight them not uniformly. And the Hamming and the Hann filters examples of filters where we have a rolling window, but we don't weight the samples in the window equally, we weight them unequally. And they're weighted by these two functions here. The one on the left is a Hann function. The one on the right is a Hamming function. The shape of the weighting are plotted downstairs here on the left and the right. So in this case, in this example, the full width of the window, which we're calculating a rolling average, weighted rolling average now, is 50 samples. The samples in the center are weighted more, so right in the center We're weighting those samples more. Right in the center, we're weighting those samples more. The samples towards the edge of the window, we're weighting less. And actually, in the Hann filter on the left-hand side, as you go towards the edge of the windows, the weighting of the samples vanishes, goes towards zero. In the Hamming filter, the weighting goes to not to a much smaller weight, but not to zero. So those are the differences. It's actually the same equation that's used for the weighting. You look on the left and look on the right, but the equations have a parameter in them. And the parameter is different in the two cases of the Hann and the Hamming filters. Now, I'm not explaining how these filters were derived. Obviously, Hann and Hamming derived these filters. Hann and Hamming derived these filters to optimize this transition from passing low frequencies and attenuating high frequencies. So they're designed to optimize the selection of isolation of signal from noise when you've got a low frequency signal on a high frequency noise. So that's the purpose. And we'll see that they perform better than a simple rolling average. Okay. This slide, I tried to compile all three of these convolving filters that we just talked about, the unweighted, the ordinary rolling average of nearby samples, and then the weighted average of nearby samples in the Hamming filter and the Hann filter. So on this plot, on the left-hand side, I'm just plotting the convolving function that's used in the filter. It's the function that determines the weights in the averaging of the samples in the filter. And so the top plot is just equal weights of all the samples in the window. And so that top plot is just a horizontal line as every sample gets weighted equally. And then in the center on the left and in the bottom of the left are these weightings that we just talked about for the Hann and the Hamming filters, where we're going to weight the samples in the center more, we're going to weight the samples at the edges of the windows less. And so these are the distributions. If you take the Fourier transform of these weighting functions, that tells you the frequency response of these filters. And so that's what's plotted on the right-hand side are the three corresponding frequency responses based on these different rolling averages, the ordinary, unweighted, the Hann and the Hamming rolling averages. This particular window width of n samples yields these frequency responses over here on the right-hand side. Just to make the main points, right, on the frequency responses. At the center of the plot is low frequency. So the 0 Hertz is right on the center of the plot. So these are Fourier transforms. If you remember back to Fourier transform, when you take Fourier transform, you just get the Fourier transform of your real signal in your time domain is a complex quantity in your frequency domain, and the Fourier transform is actually mirrored on the left and right of the low frequency, the 0 Hertz point. And so here's 0 Hertz right at the center of each of these three plots. And all of these filters are passing through low frequencies and are going to attenuate high frequencies. So you see that they all have, this is a unit for attenuation. If it's 0 here, then the signal is going to pass through. If it becomes more and more negative, the signal is going to be attenuated. And so you see the signal passing through at low frequencies. And then as you walk away to the left or the right in any of these plots, you see that the signal is strongly attenuated. And you see that attenuation is larger in the Hann and the Hamming filters, these two here on the center and on the bottom right, than it is in the simple, ordinary, unweighted rolling average, this one upstairs here. So that's the purpose of introducing these, is to have this much faster transition between a signal that gets passed and a signal that gets attenuated. Another feature that you see in these plots is, you can probably make it out, is this little high frequency structure in these plots. And it's in all of these plots to greater or lesser degrees. Think about the ordinary weighted average in the rolling filter. If you have a period of a signal that exactly matches your window over which you're calculating the average, so if the period matches the window size, then that signal can't get through that filter. When you carry out the average over the window, because that window corresponds to one period, the average is going to be 0. Or if the frequency is such, or the period is such, that there's 2 complete cycles in your window. Right? When you average those 2 complete cycles in your window, then that signal will also not get through the filter. And likewise for 3 cycles in the filter, or 4 cycles, or 5 cycles, those signals at those particular frequencies that are harmonics of the window size won't get through the filter. And so that's the cause for this sort of fine structure, this high frequency pattern in this upper plot here. It's a little bit more complicated when you're not weighting equally, but you can imagine that it still applies when you're not weighting equally. So you see the patterns here. Okay. So those are the those are the time domain filters that I wanted to introduce. Big differences from the RC filters is that these are convolving filters. They just depend on the input. They don't have any feedback from the output. Another big difference is that in the recursive filters, the RC filter, really we were just taking one input sample, the current input sample, and the prior output sample, and combining those. It was kind of simple in terms of the calculation. In these cases with the window filters, depending on how big or small your window is, you might be making a large-scale calculation for every output sample, because you're averaging over, and maybe it's a weighted average over many input samples. So these are more computationally intensive, but what these more computationally intensive filters give you is a much greater discrimination between passing a signal and attenuating noise. The transition from passing the signal to attenuating noise is much sharper, much more defined. And actually the noise suppression is much deeper. So that's the advantage of them. I'm going to go to my code, and we'll look at implementing a simple unweighted rolling average filter. We'll look at implementing the Hann and the Hamming filters, and we'll look at the frequency response. I'm going to be using several functions from a Python package SciP. We've talked about that before, I think, when we were doing random numbers and other things. We use that package. Within that package, within that library, there's a kind of sub-package that has a lot of signal processing functions, modules that you can call. And so that's a very useful resource when analyzing data, when interpreting data, is this SciPy signal package. And that's where we'll find the tools that we need to make a rolling average filter, make the Hanning and the Hann filters with really very little work and just a few lines with the modules, with the functions that are in SciP. I'm specifically going to use a function called convolve. I'll say more about all the arguments of it when we get to seeing it in the code. But this is the function I'm going to use to apply the apply the window, to do the convolution of the window with the input signal to get the output signal. I'm going to use convol. And I'll be using that whether my window is just a regular unweighted window or my window is going to be a Hann window or a Hamming window, those different variants. The other things that I'm going to use are this is a nice package. It has a function. You don't have to calculate that. And weightings for all your samples in your window. We can just call a function that will do that for us. We also don't have to calculate the Hamming weightings for all the samples in our window that we're going to average over. We can just call a Hamming function. So we're going to use these two here. And again, I won't go through the arguments. The arguments are pretty simple to these Hann and Hamming functions, but we'll just go ahead and use them and implement them. So this means that with the convolution function for all our windows, with Hann and Hamming functions for our particular windows, most of the work is done for us. We've just got to embed those in the calculation that we want to perform. Okay. Here's my code. I'm importing a bunch of functions here because I wanted to do some plotting. I wanted to look at these signals inputs and the signal outputs in both the time domains and the frequency domain, so we can get a better understanding. So I wanted Fourier transforms. And then we wanted to be able to apply these different filtering techniques. We wanted Hann windows, Hamming windows. We wanted the convolution function to apply that. So this is all the packages that are imported here. In particular, here's the new one. We've not met this before. This is the signal package within the SciP library. Or maybe it's the SciP signal library within the SciP package. I don't know. Okay, so here's my code. Just for one cell of code in which I'm going to generate a input signal. I'm going to make it a simple sinusoidal input signal. I'm going to pass it through the filters, the rolling average filter, the Hann, the Hamming filters. We'll pass it through those filters. And I'm going to calculate the output signal. And then we can compare the input signal with the output signal. I'm also, when I calculate the input signal, I'm going to calculate a Fourier transform of it. And when I get the output signal, I'm going to calculate the Fourier transform of that, so I can compare in the frequency domain the input signal and the output signal, as well as in the time domain. We'll obviously be comparing the input signal and the output signal. So that's the scope of this cell. Make a signal, calculate its Fourier transform, pass it through the filter, determine the output signal and its Fourier transform, and then make some plots comparing. There's a number of parameters in all of this. There's parameters associated with my discrete time space that I'm going to work in. There's parameters associated with the signal that I'm going to pass through the filter. And then there's parameters associated with the filter itself. So I've got a bunch of parameters, and we're just going to investigate a little portion of the full spectrum of all the parameters. And then, as well as defining those parameters, I've obviously got the code for applying the filters and calculating the Fourier transform. So I just want to walk through all of that. First two lines are defining my sort of proxy for a independent variable, proxy for the time variable, a discrete space of time intervals. So I'm going to have units of time, so seconds, 1 second. I'm going to think of a duration of time of 1,000 seconds here. And I'm going to make a proxy for my independent variable, which is just those clock ticks from 0 to 1,000 in steps of 1. So that's TI. I'm going to create a input signal that is just a sinusoidal signal, simple sine wave. It's going to have an amplitude that is an adjustable parameter. It's going to have a frequency with an adjustable parameter, and we'll play with that a little bit. And then I put in a phase too, but I'm just going to leave the phase at 0. So it's a parameter that I'm going to touch. And so I define the amplitude as you would for a sinusoidal signal. I'm going to define its amplitude. I'm going to define its frequency, and I'm going to define its phase. And then I'm going to make my input signal. So I call the input signals xi's. I'm going to call my output signals yi's. I call the Fourier transforms of my input signals f for Fourier transform xi, so fxi's. I'm going to call the Fourier transforms of my output signals, I'm going to call them yi's being my output. Anyway, so I initialize a input signal as these n equals 1,000 samples, and I fill it with a sine wave of the amplitude and the frequency and the phase that I've specified. And then right off, I using the Fourier transform package inside I calculate the Fourier transform, and I put the calculate this quantity here, which is the axis, the frequency axis for the Fourier transform. And if you remember, we got used to slicing the Fourier transforms to get rid of the mirroring, so that we just look at one copy of the histogram. And if you remember, the frequency range goes from the lowest frequency 0, and the highest frequency is the Nyquist limit, which is half the sampling range. So that's the range of frequencies that we would expect. Okay, so at this point, I've just got I got a independent variable for time. I got a input signal, which is a nice sine wave. I've defined those two things, and now I'm going to set up the filtering, which is done in basically the filtering setup is done in this block of code here, and the actual filtering is done in this couple of lines here. So if I'm going to define the rolling average filter, or the Hann filter, or the Hamming filter, I'm going to specify a filter width. How many samples of the input am I going to calculate the unweighted average over? Or how many samples of the input am I going to calculate the weighted average, the Hann or the Hamming weighted averages over? So I'm going to define a number of samples. And I define that as 11. All my samples are going to be odd numbers because I'm going to center them on the convolute function will center those on the input signal, so that the average will include the average at the ith tick will include the ith sample, and then an equal number to the left and right of the ith sample. That's why I'm picking odd numbers. So this is the number of samples that I'm going to do some sort of average over. And then these three lines here, two of them are commented out right now, and one of them's not commented out. These three lines correspond to defining the weightings that are in the windows for the sample. So in the case of just a simple rolling average, where I want a equal weighting of all the samples, I'm just using this function to construct an array. I mean, I could have done this with ones, which we've done before, but I'm just constructing an array of length, the window size, so 11, with values that are given by this element. So this constructs a window that has 11 elements with equal weighting. And down here, I'll normalize it so that the sum of the elements equals 1. So that's a window that would correspond to the simple rolling average, if I just run that code. If I want to replace it by the Hamming window or the Hann window, it's very simple if I use the SciP package that we've imported, because there's a Hamming function and a Hann function. You just call them with the number of samples in your particular window, and it will give you it will return an array or list that contains the weightings for those samples. So in top case, I'm constructing myself the weightings of the 11 samples. In the second two cases for Hann and Hamming, I'm just calling the user function, a library function to return those weightings. And again, I normalize them all so that the sum of the weightings is equal to 1. That means that I'm not multiplying overall. I'm not multiplying the input signal when I get the output signal by some amount, or dividing the input signal to get the output signal by some amount. The gain overall is 1. I'll print them out so that we can see what these windows look like. So at this point, I've got through this little block of code, which was just defining a particular window, depending on which of the three lines in the middle I've commented or not commented out. Then this one line is really the application of the filter. So the entire application of the filter, once I've constructed the window, comes down calling one line, one function, is the convolute function. So the convolute function takes several, it's quite a versatile function. I won't describe all the arguments, but I'll describe the arguments we need here. These first two arguments, contain the function and the function that you're going to, when you convolute two functions, you've got two functions. These are those two functions. So we're going to convolute the input signal, that's xi, the some array in our representation, with the window, that's our second function in that convolution. And so we pass those two as arguments. There's some details to that are important when you think of a digital convolution versus sort of a analytical convolution of two functions. So what comes up with a digital function is, well, supposing I've got 1,000 elements. I've got a size 1,000 array for my signal. Now I'm going to convolute it with a window that is 11 elements. So supposing I'm in the middle of the array of 1,000 elements doing the convolution, then I'm going to, supposing I'm at sample 500. Well, I'm going to convolute using sample 500, the 5 samples to the low side of that, so 499, 498, 497, 496, then 5 samples to the high side of that. And all those samples exist, so I can just calculate the convolution. But what happens when I'm at the very first sampling? Maybe what happens at the very last sample in the array. I'm at sample 0 in my signal array. I want to convolute it with my 11 sample window. Well, the convolution will look at the center of the window will be set at the 0 sample that exists. So I'll include that in my weight. To the right, to later times in my input, there are samples that exist. There's the first, second, third, fourth sample. So I can include those in that way. But to my left, that's looking before the first sample. There are no samples. So what do I do? There's various options for what you can do. One thing you can do is just add the input with extra zeros so that the convolution still works on the first sample, second sample, third sample. It's just convoluting with kind of padding of zeros. And so that's what this same argument does. When you pad the ends of the input with extra samples so that you can carry out the same weighting over the full range of your input samples, that will give you an output that has the same size as the input. And that's why this argument, this code is called SAM. To get an output that's the same size of the input, so that yi will be the same size as xi, you have to pad xi on the far left and on the far right with extra zeros so it can actually compute a weighted average of the window, convolute the window with the input. So that's one way of dealing with the bookends, basically, on the far left and far right of your digital trace. There are other ways to do it, right? You can say, well, I'm not going to go right to the far left or right to the far right of my input sample. That creates that avoids the problem of having a pad, but it means that your output has less samples than your input. So that's the disadvantage of that approach. And that's a different argument. But the one I picked is just to create an output sample that's the same size as the input sample. And to do that by this padding technique. The reason I did it, to have xi and yi the same size, is just a matter of, I want to plot these things, and I want the sizes of the arrays that I'm plotting to be the same size arrays. So it's just convenient for the plot. But we should bear in mind that the first few samples in the far left and the far right are calculated based on padding. Okay, so the two signals that I want to calculate the convolution of are the first two arguments. We've got to say something about the females, the mode of the convolution, how to deal with the bookends at either end. There's various ways of doing that. Within the function, then just returns the output. And downstairs here, I just calculated this Fourier transform, again, stripping off the mirror. At that point, we generated our input signal and its Fourier transform. We passed it through the filter, and we can look at the output and its Fourier transform. And so I'm just going to create a couple of plots. The first one is time domain, and the second one is the frequency domain. In each of the two plots, there are two curves. In red is the input signal, and in blue, in green is the output signal. And that's true in the other plot too. Now, let me just roll back up and remind us, in this example, my input signal had a frequency of 0.02. So frequency of, it says, 0.02 sample, so 0.02 cycle per sample. So one cycle would be a period of 50 samples. I've got a time range of 1,000 samples, and so this frequency will correspond on our plot to seeing 20 cycles of the input signal. That 20 samples of the input signal is, so that period, 20 samples, corresponds to a longer period than the windowing. The windowing was 11 samples. That means that the frequency of my signal for this longer period is lower than the corresponding frequency, the frequency that will correspond to the windowing, which is a period of 11 samples. So this case I'm looking at is a low frequency, set on the scale of the size of the window. And so we expect this to go through the filter. And so let's just see, with that sort of background, how it goes through the filter. So red is the input, green is the output. We see that the signal has passed through the filter, and we've got a signal at the output that has almost the same amplitude. It has slightly reduced gain from the input. So this, as we expected, with this size window in this size frequency period, this is a low frequency signal according to this particular rolling average filter, and is basically passed through the input. It's just slightly attenuated. And if we were to make the frequency even lower, it would be even less attenuated. If we increase the frequency, and rerun this. Now if I change the frequency to 0.2 rather than 0.02, that means that the period, whenever the frequency, is going to be 5 samples. So we would have 200 complete oscillations over our 1,000 samples. That 5 sample period is shorter than the window size, or equivalently, that the frequency is higher than the corresponding frequency of the window. So this signal we'd expect to be attenuated. And well, look, here you see the frequency is very high. We can barely see the oscillations. There's 200 oscillations in this time range. The red is the input again. The blue and green is the output. And so this is strongly attenuated by this filter. So that's something we expect. We could see that in the time in the frequency domain also. The red is the input, the green is the output, and well, it's the same frequency for the signal on the output as on the input, but we see that the amplitude in the frequency spectrum is correspondingly reduced, just like it was in the time spectrum. If we were to go back to the original frequency, and look at the signal, input signal and the output signal and the frequency domain. Firstly, we moved from 0.2 hertz frequency here to 0.02 hertz frequency over here. But also, if you look at the red and the green frequencies, the amplitudes of those frequencies, the green one is only slightly smaller than the red one. So again, that shows you that that signal was largely passed through the filter. Okay, so that was a simple unweighted average filter, the simplest rolling average that you could construct. And it does act, big picture, the big point is it does act effectively as a rolling, as a low frequency filter, passing low frequencies, attenuating high frequencies. But instead of having a time constant RC set by a value of a resistor or capacitor, it has a time constant that's being set by the window size. That plays the role of RC, is played by the window size. Let's change to the Hann and Hamming. So we'll run the same thing with the Hamming filter. That's the only change I made there. I just commented out the unweighted rolling average and put in the Hamming weighted rolling average. And we'll go down and look at the two plots again. This is the plot in the time domain, in red, the input signal, and green, the output signal. You see again that the alpha signal is basically transmitted through the filter. And actually, it is reduced a little by this filter, but even less than the unweighted rolling average. So at low frequencies, we'll see the Hann and the Hamming filters do better in transmitting the low frequencies. They distort the low frequencies or attenuate the low frequencies less. And then we're going to see at high frequencies, they do opposite. They do better in attenuating the high frequencies. So this difference between the output and the input is much closer. The difference is smaller for the Hamming filter. And you see that in the frequency domain too. These two spikes on the left-hand side of the plot are very similar. That was Hamming. And just Hamming, just slightly different weightings of the samples in the window. They both weight the center more, the outside's less. One of them, the weighting goes to 0 at the outsides of the windows, and one of them it doesn't quite go to 0 at the outsides of the windows. If we look at this one, I think this one has the best performance. The output in green, the input in red are almost overlaid. It's almost perfectly transmitted this input signal. And you'll see that in the frequency domain too. If we now go to the high frequency, so 0.2 hertz, period of five samples. That's smaller than the window size of 11 samples. This is going to be attenuated. Let's look at the attenuation of the Hann and the Hamming filters. Remember, it was attenuated by the unweighted rolling average, probably by a factor of 5 or something like that, maybe a bit more. Let's see what the Hamming and the Hann do for this signal. Here's the Hamming, and this is much better performance in terms of attenuating the input than the simple rolling average was. We've only got a few percent of the signal less. So this is, again, this idea that this will be a more effective filter is much more efficient at maintaining the signal at low frequencies and extinguishing the signal at high frequencies. We of course see that in the frequency domain too. And then finally, the Hann filter, we run that. even more extinction of the signal. You see it here in the time domain. We can barely see a signal in the time domain. And likewise, if we look in the frequency domain, the two plots, can't see the plot, the green curve here, which is just completely underneath the, well, that doesn't make any sense what I said there. This plot is not telling us much. And maybe it should reorder the plotting of the green curve. Anyway, this one shows you the extinguishing of the input signal at high frequencies. I got one more cell in here. Let me just show you a little bit of it, because this is the related to the homework assignment. We could compare the frequency response of different filters by, instead of just applying the filter to a signal of one particular frequency, we could build a loop over multiple frequencies, like we did with the RC filter in the last class and in the homework. Build that loop and look at a frequency response of the filter. And we could look at the frequency response of the filters. We could look at it versus the different types of filters. We could also look at it versus the equivalent of the RC parameter, the time constant parameter, which is the window length. So I looked at an example of that here. I'm going to insert my code generating the signal and generating the window for the convolution and performing the convolution and calculating the output signal. I'm going to bed that in a nested for loop. And in the nested for loop, on the inside of the nested for loop, I'm going to walk over a range of frequencies. And on the outside, in this case, I'm walking over a range of window sizes. So the window sizes are going to change the kind of time constant of the filter, or the frequency cutoff of the filter. And the frequency loop, well, that's going to scan the frequencies. And so we did this in the last class where we were changing the time constants of the filter, the RC values, and we changed looked at the frequency response. I'm doing exactly the same thing here in this class. I'm effectively changing the RC time constant, the time constant, by changing the window sizes, and then I'm scanning over frequency. So I've just embedded the code from the last cell that I went through in detail into this nested for loop. And this is, I'm pretty sure if I remember it, this is along the lines of what you're going to do in the homework, but I want to show you the plots there so that you can see what sort of things you might expect. Where am I going? Okay. In my nested for loop, I examine this frequency range here, and I examine three in the outer loop. I put three window sizes, here window size 11, and then two other odd window sizes. I have 21 and 31. So these are larger and larger window sizes. So greater and greater time ranges. And so they will attenuate higher and higher frequencies. They will only pass lower and lower frequencies as we increase the window size. So blue is the window size that we used in our first cell, a window size of 11. You see that it's passing, we looked at a frequency of 0.02, essentially past that frequency. If you looked at a frequency of 0.2, it essentially attenuated that frequency, so it reproduces that effect. And then I made the window size larger. I made the window size larger, which means that you attenuate more frequencies with your filter. And so you're only accepting a smaller range of low frequencies, with the window size 21, you're accepting an even smaller range of frequencies with the window size of 31. And so you see those effects here. And then you see this sort of picket fence type thing, which is this effect that we describe most simply understood in terms of just a simple rolling average filter, that if your frequency exactly matches the window width, or a harmonic of it matches the window width, then it will be completely attenuated by the filter. So you basically see the filter's width, its period or equivalent frequency, in the spacing between these dips here. Okay. I wanted to, in the last 10 or so minutes, show you one other type of filter. This type of filter is not a homework assignment. I just want to show you it so you have an idea of it, because it's an interesting way of getting very high performance filtering. And it's filtering not in the time domain. So in the RC filter, we worked with the time domain signal. It's time domain filter. With the rolling average, Hann filter, Hamming filter, we're working with the time domain signal. So everything we've done so far is in the time domain. But you might think, well, we met earlier on Fourier transforms between frequency and time domain and frequency domain. If I want to reject, say, high frequencies, extinguish those and keep low frequencies past those, why don't I turn everything from the time domain into a frequency domain and apply a frequency cut in the frequency domain, where I can make that frequency cut in the frequency domain extremely sharp? Why wouldn't I do that? Well, you can do that, and that is done. The challenge with it is that you can only do it in some applications. So the RC filter that we worked with, and the digitally, and the rolling average Hamming filters that we worked with digitally, they can be applied in real time on a real digital signal. Because they are applied sample by sample on the input to get the output. If we want to say, well, why don't we just take our time domain signal and convert it into frequency domain signal and work there, we have to have the whole time domain signal to convert into a frequency spectrum. And so in some applications, you're using digital filtering in real time, this is not applicable. In other applications, you have your time spectrum and you can work and turn it into a frequency domain spectrum. So the basic idea is shown on this plot here. We're going to take our input signal in the time domain, we're going to Fourier transform it with a Fourier transform package into the frequency domain. In the frequency domain, we'll then process our frequency domain data. And the most obvious example is I could, in the frequency domain, say I'm just going to keep the frequency below a certain frequency cut and eliminate frequencies above that frequency cut. That would be a simple implementation of a low-pass filter in the frequency domain. It's just accepting the ones below cutoff frequency and rejecting the contributions above that cutoff frequency. I do that, and then I convert back from the frequency domain to the time domain, and that's my filter. And I'll show you with this example here. I'm going to build a signal that is a signal that contains two separate frequencies. One's going to be a low frequency and one's going to be a high frequency. Just an example of being able to reject relatively closely spaced one frequency and keep the other frequency, even though that they're relatively closely spaced in terms of what we've been able to achieve with low pass RC filters and Hamming rolling average. So we're going to start with a signal that has two, this has two frequencies in it. We're going to Fourier transform it, and that time domain signal will become in blue here, this frequency domain signal. This frequency, it's a little hard to see, but I haven't removed the mirroring here. There's two spikes on the left of the origin here, two spikes on the right of the origin. These are the two different frequencies, which is mirrored. I'm going to apply a cut in the time domain, in the frequency domain, or I'm going to apply a mask in the frequency domain. A mask in which I keep the frequencies that are lower than these red lines and reject the frequencies that are above these red lines. So just like multiplying by a mask, multiplying this array by a mask is either zeros or ones, is ones below a cutoff frequency, it's zeros above the cutoff frequency. That's going to be my new filter, my frequency domain low pass filter. So I'm going to apply that filter. I'm going to reject these as peak to the far left, as peak to the far right. I'm going to keep the ones that are closer to the origin. And then I'm going to convert back. I'm going to do an inverse Fourier transform and extract my original signal, the lower frequency in my original signal. So that's the idea. So just to show you the implementation of that, it's this code here. Let me just walk through this a little bit. So I'm going to walk through this. We've only got 5 minutes, fairly quickly. Going to define a discrete time, a proxy for an independent variable here. 1,000 ticks, 1 second ticks, as we've done before. I'm going to define 2 sinusoidal signals. One is signal number 1 with amplitude 1, period 1, and then a second signal with amplitude 1, period 2. The amplitude, sorry, the period of the first signal is 25 clock ticks. The second signal is 50 clock ticks. So they're different by a factor of 2. So these are our 2 signals. They have 2 corresponding frequencies that are different by a factor of 2. I'm going to calculate here the sinusoidal signal that correspond to these amplitudes and these frequencies. So that's the x1 and the x2. I'm going to add them together. In my code, I got some possibility of adding some noise. I'm not doing this in this code. So I add these 2 signals together. So at this point, x is a sinusoidal signal that contains 2 frequencies that differ by a factor of 2, and that's going to be our input. And I also calculate the Fourier transform of it here. And I think in this cell, I just plot that input. These are the combined 2 pair of signals, 2 different frequencies, and you see very clearly in the Fourier transform that they have 2 separate frequencies. Okay. Then in this cell, I apply my filter. And my filter is basically that I'm going to make take the Fourier transform. The Fourier transform the input signal is f of n. And I'm going to make a copy of that Fourier transform. But I'm only going to keep the frequencies that are below some cutoff frequency. And I'm going to reject here in this line, set to 0, any frequencies above the cutoff frequency. So this is the applying of the filter, and this is called the brickwall filter, where I keep low frequencies and I'm going to reject higher frequencies. And F cut I define to be halfway between my lower frequency and my higher frequency. So I'm going to calculate a new Fourier transform with the cut applied, and then I'm going to compute the inverse Fourier transform to find out the signal from that. And so here is the output signal from the that filter in the frequency domain. And here is the frequency spectrum. It just has the lower frequency in it and not the higher frequency in it. So we would compare this with a starting point up here where we have both frequencies in the time domain and the frequency domain.